Good morning. Our project is called Experimental Replication of Shoreline Erosion and Landslides in a Laboratory Setting Using a Multimodal Device. The presenters for this project include Brett Steck, Makila Heber, Esther Janinga, and Payne Sanders. The mentors that helped out on this project are Juk Bhattacharya, Oscar Yabusetin, and Haijin Soon. A quick introduction to our project. For this project, our main focus was on replicating the erosional process along the Lake Michigan shoreline. Being a multi-field project, this presentation focuses almost exclusively on the physical application of the project. The second half of this project was technology-based, which utilized computers and sensors created by the Physics and Computer Science Department. Erosion along Lake Michigan shoreline tends to increase during springtime, potentially leading to landslides. This can be caused by the moisture content percolating through the material, which might create weakness. As seen in the picture on the slide, landslides on Lake Michigan are a serious problem that needs to be addressed.
Landslides are caused from a slope failure when extra water is added to sand in real life as snow and rain. These diagrams show what happens when water seeps within sand and freezes to form ice, which expands the spaces between the sand grains during the winter. When the ice thaws in the spring, the water moves along the expanded space and causes slope failure. The failure envelope depicts the breaking point for which the sand has a greater force separating it than the force compacting it.
For this project, we used a Raspberry Pi. The Raspberry Pi stores the data that can be used in graphs. The parts of the Raspberry Pi include 4 soil moisture sensors and 4 digital sensors.
When deciding how to set up our experiment, we had to take into account several variables looking specifically at real-life applications. Such variables include the water level of the lake, porosity of the soil, different layers within the soil, average temperature, and the average moisture content, which can be affected by rain and snowfall. To replicate these variables in the experiment, we used different water levels in our experiment container for the erosional process, and sand as the dominant material around the shorelines. We created different layers of saturated and unsaturated sand, along with a layer of ice to replicate the changes in seasons. Unfortunately, we were not able to replicate the average temperature inside the lab.
The supplies that we used were sand, which was purchased from Sandtastic, a storage bin that could hold the experiment, a tin pan to form our base layer and to be the foundation for our model, a scale to weigh the sand and water ratios, liquid nitrogen to quickly freeze the layer of water to form ice, saran wrap to wrap the sand cliff so water didn't trickle outside of the model of the experiment, and deionized water for our makeshift lake and different saturation levels. To start our experiment, we filled the plastic container with 2.5 centimeters of water. This was to mimic the natural erosion process that takes place on the shoreline of Lake Michigan. Because of the erosion from the standing water at the base of the experiment, the sand became unsteady, thus causing a landslide. Next, we oversaturated the sand at the bottom of our makeshift cliff because that represents the area that is the closest to Lake Michigan. The second layer represents the process in which the moisture moves from a saturated zone to an unsaturated zone. The third layer is used to depict the accumulation of water during winter. The ice layer, layer 4, represents frozen ground during winter, which will add to the water table as the ice melts. Finally, the fifth layer was oversaturated with water. This was so we could see the moisture travel through the layers, which would eventually increase the lake level.
When it came time to testing our model, we played around with the different layering. We measured the sand layers by weight rather than height because we would not be able to account for sand's tendency to compact. This compaction would cause a shift in height and would disrupt our measurements. Once we decided on the appropriate layers, we ran the experiment several times to confirm that we could make a slide occur. After establishing consistent erosion patterns such as crack formations viewed in the picture on the left and undercutting viewed in the picture on the right, We began implementing moisture sensors to track the motion of water through the soil. This allowed us to predict where slope failure would occur.
In our model, we began to see the formation of cracks and creeping motion of the sand, which portrays the real-world processes that occur along the Lake Michigan bluffs. When too much water percolates in the sand, the pore pressure of the water increases. This then separates out the sand grains and makes the overall slope weaker. When external weights such as buildings and tall trees are added on the sand, failure can occur. In addition, undercutting at the base of the slope is a result of rising water levels and waves crashing along the shoreline, which eats away at the slope. The crashing of waves drags sand back out in the lake, weakening the bottom of the slope and alters the stability of the slope.
As our experiments progress, we plan to alter several variables to better represent the shores of Lake Michigan. Regarding the material we use for our cliff, we are considering including clay layers within the sand, which would provide an impermeable surface so water would flow horizontally rather than vertically. Another idea we have is to change the material to playground sand, which contains a variety of different grain sizes. This would change the permeability of the sand, which may alter the occurrence of slope failure. In addition, we will begin using a strain gauge to more accurately track the movement of material as it separates from the cliff. We also want to use the moisture sensors more consistently and accurately measure the weight of each layer to better understand the effects that temperature and moisture content have on slope failure. Lastly, we hope to begin field testing come summertime to see how our theories and equipment work in real-life situations.
Ultimately, this project is important because of the safety precautions that can be taken by monitoring the shorelines that are subjected to erosion patterns. This project aims to protect lives and property damage from shoreline erosion. By knowing the rate at which the water seeps through the material, the moisture content after the freeze-thaw cycle in the spring, and the movement from saturated to unsaturated zones that make slopes unstable, we can prepare for possible erosional areas. This project not only applies to the Lake Michigan shoreline, but also to all coastal areas across the globe. We expect that this project will continue and advance in the coming future so that we can predict landslides and mitigate damages. Thank you for listening to our project today. We would love to hear any questions or comments you may have.